Thanks for coming out, everyone. It's a real privilege to be here tonight. And we've got a lot of fun things to talk about. Ideally, now there will be death by PowerPoint at first, but hopefully the second half of tonight's presentation will include a lot of pictures, satellite images of the weather here over Alaska. Ideally, imagery impressive enough it should sell itself. So without further ado, let's see if that works. There we go, the mandatory logo display, but moving on. Okay, guess what? Let's say you are a forecaster, and the phone rings. You have to pick this phone up. And you pick up the phone, the person says, yeah, forecaster. I'm driving in my truck. Give me a forecast. Where will I be in 1 hour? And now you're on the spot, and you say, well, I'd like to help you out, but I need some more information about, maybe where are you right now? Which direction is this truck pointed in? How fast are you going? And the person says, well, I'm in Delta, and I'm heading toward Fairbanks. Where will I be in an hour? And if you drive like Deanne, sometimes, you'll be in Fairbanks in about an hour. The point of this story, as I'm mangling it, is in order to make any kind of a forecast of the future, one must first understand the initial conditions, that's a catchphrase, the current state of your scenario now at time equals 0, or just now. You got to know where the chess pieces are on the board if you're going to try to anticipate moves in the future. This is entirely true in the weather business. To make a weather forecast, you must first understand where's that low pressure storm, where's the high pressure, where's the cold air, where's the moisture connection from the ocean. To know where those things are, and ideally, this is harder, to understand why those things are where they are. So just understanding where are the pieces on the board, then trying to fit together. You hear that phrase, models, a lot, weather models. I think the most important model is the conceptual model of the forecaster. You got to get information in your head, mull, think it over, decide then where this storm that is now here, because we know it's here now, where will it go in the future? So when that phone rings, it's nice to have enough information at the beginning to make the forecast. There we go. So the fundamental first step, I just said that. Forecast the weather in the future, you got to know where it's going. So how do you observe the weather now? Well, there's weather balloons. Those are not just for late night conspiracies. There really are weather balloons. That was my first job, full-time job in the Weather Service. They sent me to Nome, and I launched weather balloons, and that was a kick, at 35 knots of wind pulling your balloon apart as you're trying to throw it in the air. That was all. It was just like North Dakota, when I got there. We have weather radar. There's a radar in Fairbanks. And in Alaska, there's always a catch, isn't there? That the density of the radar network and the balloon network in Alaska, and surface observations, as they're called, that's to say at the airport and such, it's just, there's less observations in Alaska than other places, and because of our microclimates, like at the airport, this is classic in the wintertime, it's 29 below at the airport, and up in the hills, it's 9 below or something, all within the pretty small footprint, actually, where people live. You get so much variety. So given that we don't have many real observations, and then the topography limits the spatial representativeness of those operations. And then we've got an Arctic Ocean to the North Pacific to the south, the Russian Far East. There's a whole lot of data empty around Alaska. A cold front cannot sneak up on Chicago. It can sneak up on Barrow. It can sneak up on Kotzebue coming out of the Chukchi Sea. So how do you observe the weather given these challenges? Well, here we go, satellites. Finally, Alaska has an advantage. A satellite doesn't care if what it's looking at is a big important place like Manhattan Island or Washington, D.C., or Umiat. The satellite will give the same kind of data. And in fact, there's a certain class of satellites called polar orbiters. And guess where those go? They go over Alaska, and we actually get just an accident of the way the world works, we get more data from those satellites than Washington and Manhattan do. Nothing against Washington and Manhattan if they happen to be listening to this. Okay, so that was our little intro. Where are we going today? We're going to talk about different kinds of satellite orbits, the different instruments on those satellites, talk about Superstorm Sandy and why these polar orbiters actually do matter to everybody. It's not just, the tax dollars would not be spent to launch satellites that are called polar orbiters only for Alaska. It matters to the whole world, and Superstorm Sandy is an example. You can take this to a congressman and say, this is why satellites are important. And then where I work at GINA, that's an acronym. Hopefully I can control the acronym flow today. But we have the High Latitude Proving Ground. And what does that mean for Alaska? And at the end, we'll have some references. There's a lot of great stuff on the internet right now. I used to work with a guy at the Weather Service here in Fairbanks, and he didn't want to retire because he just loved the data, had to look at the data. And fortunately for good old Anton, right when he retired was just as the internet was really blossoming. And now, you can find all kinds of satellite imagery on the internet. It's really a great time. So let's first look at the lawgiver, as we call him, Johannes Kepler, from 400 years ago. He came up with 3 rules of planets orbiting suns, which also apply to satellites. Number 1, the orbit of a planet about the sun is an ellipse, actually, not necessarily a circle, with the sun at one of the foci. And the planet sweeps out equal areas in equal time. We'll see a cartoon of that in a minute. Then number 3, the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. Okay, there will be a test after this. Actually, no, for our purposes today, let's forget about number 3, but these first 2 are kind of important. The orbit is a ellipse, not necessarily a circle, but a circle is a tight ellipse. And a planet sweeps out equal areas in equal time, and what that means is when a planet is closer to the sun, it moves quicker. When it's further from the sun, it moves slower. Our Earth takes 1 year to go around the sun. That's convenient. We decided what a year was, and it's our planet, so it's 1 year. Jupiter, further back, further away from the sun, takes 12 of our years to make 1 lap on its track around the sun, because it's further away. And that's related, and really you can take that to number 2. And here's Kepler's second law. So we have an ellipse here. Here's one of the foci, and then here's the other one, invisible. But if this were the sun and this is a planet, you'll see how the planet kind of slows down, and then as it gets closer, it speeds up, and then it slows down a little bit, and these little wedges are equal in area. And so you have an equal area in there in equal time. That's Kepler's second law. Basically, you move quicker when you're close to the thing you're orbiting. And blah, 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 blah. We care about this because this also applies to weather satellites orbiting the Earth. So what kind of satellites are there? There's the geostationary orbit, sometimes referred to as GOES, geostationary, LEO, L-E-O, low Earth orbit, and this is what we call polar orbiters. HEO, highly elliptical orbit. Those don't really exist yet as weather satellites, but boy, that'd be great if we had those. And lastly is the EIEIO, that's the old McDonald orbit, but we don't have time to really go into detail on that. So the GEO and the LEO. Here's a geostationary satellite is about 36,000 kilometers out. That's the green path. A polar orbiter is much closer. It's really close to the planet, and this is where the space shuttle goes, the International Space Station. It's actually not that far up. Why put a geostationary satellite out there? Well, the further, again, Kepler is in charge, or his findings are, the further a satellite is from the Earth, the slower it orbits. These polar orbiters, anybody see the movie Gravity? Yeah, and they mentioned that the big swath of junk coming around was going to come by again in 90 minutes. That's about right. Up at the elevation of where the space shuttle is working on a telescope, or the International Space Station, that's where polar orbiters live. Those guys make 1 lap around the planet in about 90 or 100 minutes because they're close to the Earth. So they go all the way around and come back to where they started in only 90 minutes. This guy takes 24 hours to go around the planet, but guess what? Our planet spins once every 24 hours. So if you park one of these guys out right over the equator at that magic distance from the Earth, it will orbit the Earth as, I gotta do this right, it will orbit the Earth, as the Earth spins. In effect, if you park it, you put it over the equator, it will orbit the Earth at exactly the same speed of sweeping out radians as the Earth turns, in effect hovering. Now that only works if you park it over the equator. If you were 36,000 kilometers up here, you'd have a big orbit like that, and that wouldn't do you any good because the planet's turning that way. But this way, that's how you get GEO, is geostationary orbit. It in effect hovers. Whoops. Okay, and here's what they look like. In the United States, we've got 2 of them, goes east and goes west, young man, and they have views that look about like that. And The advantage of geostationary satellites is you can see a full disk, and if you have a constant frame of reference, if that satellite is in effect hovering over one place, you take a picture, you take another picture, you take another picture, you put them together, you have a movie. This is taken from a GOES satellite. Check it out. And you've got all these frames going by. Here's the time going by. Those are minutes. So every 15 minutes is an image going by. And notice how the point of view of the camera taking this movie doesn't move. And you've got that constant frame of reference. It's hovering, in effect. This is from GOES West, NOAA satellite GOES 15. And so that's kind of neat. That's the advantage of GOES. And we'll put that away. Okay, neat. Too bad that didn't work, but I'm apparently too flustered to figure it out. But there's a reference to this at the end, and here's the link for all who can get to it later. This is an image from geostationary satellite GOES West, and this is what's called the full disk. And it's way out there. It's tens of thousands of kilometers out, so you can see from Antarctica all the way up to where we live here. This is visible imagery from 1800 Universal Time on April 17th, 2014. Nothing special. That's just when I grabbed the picture. And this is visible imagery, so guess what? It's night over here, but it's daytime over here on the planet. This is the same exact time looking at infrared. We're seeing temperatures here. And again, Alaska's up on the top. You can go all the way. There's Hawaii. So that's kind of neat. Now, the bummer, though, is Alaska's up on the top of the world. So it's a little bit like trying to looking at Alaska from a geostationary satellite, since they have to live over the equator, is like reading a book holding the page kind of like that. So you'd rather have the page flat or perpendicular to your line of sight, but you deal with what you deal with. I mean, it's not a conspiracy. It's just these geostationary have to live over the equator. So that's the disadvantage here. You get a coarser resolution in space. The pixel degrades as you go further north. You also have parallax problems for clouds, weather systems that are vertically gifted. They build vertically that, because of the look angle of the satellite, you can think a cloud is in the wrong place in XY space if it's too tall. That's parallax. And then, there's all these things that don't work. Instruments on the polar or on the geostationary satellites that don't work beyond like 50 degrees latitude, which is roughly southern Canada. Out of luck for us. So the solution is the low Earth orbit polar orbiters to the rescue. Oh yeah, here's a movie loop. I should just look at this. This is a 24-hour movie loop from the summer solstice, visible imagery. There's Barrow up there, Anchorage down here, Fairbanks in the middle. And note how this is June 21st of, I think, it says down here, 2013. So now the sun's going to come back up. But how the sun doesn't set. But look how Alaska's kind of squished, and especially on the North Slope, we're really fuzzy here. So this is kind of fun. We've got that constant frame of reference to make the movie loop work, but the resolution isn't real nice. And actually, we got some convective clouds here that are demonstrating some of the parallax problems, too, because those are big convectors that then spread out. Fun stuff. Fun imagery. Again, a nice cartoon. We have a reference at the end to the COMET program. You can get at this stuff. Make yourself an account at METED, Meteorological Education. Lots of courses on there on the internet if you're interested. But again, showing the difference between the closeness of the polar orbiters and the farness of the GOES. So the LEO pros and cons. A LEO bird goes right over Alaska. If this is the Earth, the satellite goes like that and the Earth turns under it. So no matter where you are, eventually, if you wait long enough, that thing will go right over you. It's so close to the Earth, it's like getting a close-up view. You get finer scale spatial resolution, none of this parallax problems. And actually, the high latitudes, like Alaska, we get multiple passes a day from any one satellite. These satellites, these polar orbiters, go over the equator twice a day. They go over us, like northern Alaska, 8 times a day or something, so we get more than somebody else does. The bummer is, so you don't get a constant frame of reference. So you can't play those movie loops very easily. And sometimes the edge of the image just cuts off right where you wanted to see something. If the disadvantage of a geostationary satellite is that you're looking at Alaska like this, with a polar orbiter or a LEO, you're looking at it straight on, but it's here, and it goes right by. So you see little stripes. So nothing's perfect. You got to have multiple tools. And highly elliptical orbit, they don't yet exist as a civilian weather satellite, and the people I've met in the Air Force, I don't think the military has them either. Sirius Satellite Radio uses this, though. They've always got a satellite parked over well, it's not parked, but they've got one hovering over the lower 48. They do this by using a highly elliptical orbit. The Canadians may, though, come to the rescue. Polar communication and weather, if they launch this, maybe by 2020, maybe, boy, that'd be great for Alaska. I can't wait. What is a highly elliptical orbit? Okay, here's your planet. A Geo is way out here. A Leo is like this. What if, remember Kepler's first law, an ellipse with the sun or the planet at one foci. What if you made a really highly elliptical orbit where the satellite went way up here and then came down and was really close to the planet here, so it zips on by and it goes like that. It would in effect hover over the North Pole. And if you had two of them following each other, there would always be one looking right down at Alaska from above. You'd have 100% in time coverage of the North Pole north of like 50 degrees latitude, which is where we live. Boy, can't wait. I don't know, we'll see. So now we talked about the orbits and now the satellite instruments. There's a variety of instruments. Some of them are called imagers, which is a big dollar word for camera. And they have many different channels looking at different slices of the electromagnetic spectrum. Visible light is like 0.6 microns in length, and infrared is longer than that, like 10 microns that's the wavelength. You got to look at each little slice because no single wavelength, no single channel tells the whole story. It takes a village, but it does. It takes all the different wavelengths put together can give you a lot, and we'll look at, that's where the future actually of weather surveillance through weather satellites is combining multiple images, multiple channels into one image. It can be very powerful. And here's again a GOES image. And okay, this is visible, this is infrared. Visible, infrared. Whoops. Down here, there's some clouds off of Chile that are almost the same temperature as the ocean. So from infrared, which looks at temperature, you can't tell where the clouds are. There's clouds here. Invisible, it's obvious. They're right here, and then the dark stuff is ocean. The light stuff is clouds. You can see it in the visible, but you can't see it in the IR. But guess what? It's dark over here. You can't see anything in the visible, and you can see some clouds in the IR. This is an example where you need both. You need infrared and visible, and then there's different kinds of infrared and so on. That's where we go. Here's another fun case from April of 2012. This is a bit of a skewed view. So Barrow is up here. Fairbanks would be right about down there. And look at this patch of clouds up here. Okay, this is visible imagery, 0.64 micron. There's sea ice there and a white cloud. How do you see the polar bear in a snowstorm? You can't tell. But we're toggling with 1.6 microns of shortwave IR, and you can see the cloud there. Pretty nice, huh? And so the point is that different characteristics. You think, well, they're only different by 1 micron. Why does that matter? It does matter, though. The 1.6 channel is a great channel for looking at cloud top properties, and it can distinguish things that visible can't. The infrared, we were looking at infrared versus visible back on that full disk thing, looking at those clouds off of Chile. Well, here, the colored image this is infrared. Not only is this patch of cloud the same color in the visible spectrum as the underlying ice, they're both white, it's also the same temperature. So in the long-wave conventional IR, it also blends in. See, you can't see it there, but only in the 1.6 micron. So this 11 micron is conventional long-wave. You can't see it. You can't see it. Only in 1.6. 1.6 is kind of new in the weather forecasting business. So we got 3 different channels now to find one little patch of cloud. So clouds can hide, and the lesson here is you got to look at all the tools in the toolbox to see the full result. And this is why we do what we do at the university. We'll talk more about this, exactly how it happens, but we're looking at 2 images, the same satellite pass. This is Southwest Alaska, Bristol Bay here, and we're looking at April, a couple years ago, and here's the sea ice. Where's the sea ice and where's the cloud? It's hard to tell, but this image here that we make at GINA actually takes 3 different wavelengths, 0.6, 0.8 or 9, and then 1.6. You combine the 3 of them, and because of the different properties of those wavelengths, you combine them. Basically, the clouds are pink and the ice is blue. Nice. This is how you can tell who's ice and who's clouds, especially if you're on the phone with a crabbing fleet or something and they want to know where's the pack ice. We want to not get too far into the ice. This is how you can identify. Same satellite pass, but different enhancements of the the data. So we generate that and ship it to the Weather Service for their use. This is another example. If you're on Facebook, friend National Weather Service Alaska. And every once in a while they post nifty satellite images just like this. This is one that they posted last year. Again, the same, they call this false color that comes from University of Alaska here. And there's the ice edge in blue, and then these pink clouds above that. This is another case where we're zoomed into the North Slope, so here's Barrow there. This was last summer in July. Do you remember in the news there was this guy, and I've done some things in my life and never got too caught, but this guy wanted to sail solo in a sailboat, the Northwest Passage, by himself, solo sailboat, and he got stuck in the ice, and then he called the Coast Guard to rescue him. So he reported his position was up there, and the Coast Guard said, okay, we'll try to come and get you, and the Coast Guard called the Weather Service and said, where's the ice? Where's the easiest way in? They went up and got this guy, so there's the Coast Guard getting him. I mean, I can't imagine trying that. But he's a brave guy. And the Weather Service, WFO means Weather Service Forecast Office, in Anchorage, where the ice forecaster is, was praised by the U.S. Coast Guard because it was the Weather Service's assessment of where the ice is that helped them make the better ice forecasts that helped the Coast Guard go get this guy. And now it just makes a nice story. Nobody got killed or anything out there. So again, to do the forecast, to provide the service, you got to know where things are. And the satellite imagery helped out with that. Here's another sensor. This is an exciting piece of the future. This is called the Day-Night Band. And that's not a cover band playing at the Howling Dog. That is a sensor on the newest American polar orbiting satellite that was launched in October 2011. It takes every little photon of visible light available and uses it. It can use reflected moonlight, aurora, and it sees what the human eye would see during full daylight. This is actually from January of 2013 at about 4:50 in the morning. So it's dark out. And we can see the Brooks Range up there. You can see even the individual valleys. We can see, here's some sea ice up there. There's clouds north of the Brooks Range. Here's the lights of Fairbanks. Fairbanks, North Pole, Eielson, Delta, Anchorage. Down there, there's Bethel. So the day-night band can also see human lights as well as clouds. Here, this is the same image zoomed in. So here's Fairbanks. This is the North Star Burrow. And this is actually a screen capture from the National Weather Service here in Fairbanks. They gave me an account over there on the software system, so I make screen captures. This imagery was delivered to them from the university. We grabbed the data from the satellites that went overhead, turned it into a product, handed it to the Weather Service, and there it is. And they can use it. And you can even see the smudge of Delta Junction there. It's shining through thin clouds. So it's not clear, but you know if you can see a little bit of the light coming through, the clouds can't be that thick. Oh, and there's downtown Fort Yukon right there. This is a fun one. I guess we'd have to go into total darkness here to really see this very well. This is a very raw image that I grabbed from the university, but this was during new moon, unfortunately, so there's no help from the moon. For this channel to work, you kind of need some moonlight, but even during no moon, new moon, no moon, it works all right. A crabber called the Kiskasee called up in the middle of the night and said, help, we're trapped in the ice. Can you help us get out of here? And they wanted guidance from the Weather Service ice forecasters. And they said, well, what's your lat longitude? And they gave them position. And they happened to have a pass of this day-night band satellite. And there, if you can see it, there it is. That's a ship. That's one crab boat, the Kiskasee. If you can see that little dot of light. The rest of the crab fleet is down here. Here's Bethel, Anchorage, and such. But they were able to provide guidance. You can actually identify the ship and help them get out. Speaking of seeing lights at night, my parents were really great to me. I had a good childhood. The best thing, they started off right. They did not give birth to me in North Korea. And, you know, we have a lot to be thankful here for in America, but North Korea, the lights are not on, really. This satellite, this is a composite of a few passes of the satellite to try to get as much cloud-free as we can. But you can see South Korea is just all lit up at night. Here's China, Japan down here, a little cloudy over Tokyo. But look, there's the DMZ. And there's just nothing north of that. And check this out. What are these? Those are all fishing boats. And guess where the international line of agreement is on fishing rights? It's right there. So Chinese boats go right up to the edge, allegedly. This is what I've been told. And now people are wondering if they can use, this is supposed to be weather satellite, but they're wondering if they can use it for monitoring of international agreements for fishing jurisdiction and such. Here's a fun one. This is also the day-night band in the big image. And if you like this, this is the Dora Prize. We've got a poster of this out there. This is a great image. This was just back in November. This is in the middle of the night in November, and you're seeing the lights of Prudhoe Bay up there. Here's the Brooks Range. Here's Fairbanks. You can kind of see the lights of Fairbanks. There's Anchorage. This swirly white stuff, those are aurora. That's Aurora Borealis, Northern Lights. Now, the day-night band is black and white imagery, so the aurora doesn't look green or pink or anything. And down here, what's going on? Pavlov volcano is erupting. So you see that spot of light. The inset here, this is later on, this is during the daytime, so this is in the afternoon, so we're seeing now the sun is illuminating things, but you can see the plume of the volcano blowing in the wind to the northwest, and even casting a shadow, because the sun is off there. Anyway, pretty neat. Only in Alaska can you see aurora, city lights, mountains, snow, got the Yukon River right there, a volcano going off, sea ice. Did we miss anything? I mean, this image, it tells a semester-long class could be taught from this image right here, and it could be yours, so stick around to the end. This is a fun one, too. The Funny River Fire, last summer was a pretty quiet fire weather season fire season for Alaska, especially for those who survived 2004 and 2005. But we did have one fire in the state, down on the Kenai Peninsula, the Funny River. You can see the smoke plume. This is visible imagery, conventional color visible imagery from the Polar Orbiter satellite. And check this out. What happened down here? This is, again, one of the weaknesses of polar orbiters. They have an edge to the swath, and so there's just no data here. The satellite kind of took a track going like that, and it sees a little bit to either side of the track, but not forever, so it cuts off. But we can see the smoke plumes swirling and getting caught up in the circulation of a low-pressure system in the Gulf of Alaska, kind of a weak low, but that's kind of fun. You can see the smoke tracing there. Whoops. This is another channel, 3.7 micron. Look how, this is a series of movies. You can see the fire front. This is known as the fire detection channel. Again, remember, every little slice of the electromagnetic spectrum has a purpose. There's something you can take advantage of. Now, this guy, 3.7 micron, is great for finding the active fire front. Unfortunately, it cannot see through clouds or anything, so if there's a thick cloud deck over your fire, you're out of luck. But this is a succession of images, and the Alaska Fire Service folks really would like to have more of this. This is still kind of experimental, but we're trying to be able to it's a real trick. It's one thing to make a satellite product as one example. It's another thing to produce it reliably, routinely, and to deliver it in minutes. Not the next day, but it has to, the satellite goes overhead, and 20 minutes later, someone's looking at the imagery. That's what you need to serve the fire service, and we're working in that direction. It's a surprisingly difficult challenge. Speaking of fires, this is the Rimfire in California from 2013. We're toggling. So this is that fire. So this is the day-night band. You can see the fire in all the cities down here. And then the 3.7, look how, so day-night band, you can see the cities. And at 3.7, you cannot see any cities. They don't show up, not in that channel. Day-night band, you can see the fire, and you can in 3.7 as well. So that's also nice. This is that same polar orbiting satellite. It also goes over California. So look at all the stuff we've seen. Sea ice, we've seen fires, you've seen aurora, the clouds, how thick are the clouds, how much light is coming through. So much is given here. Different kinds of wavelengths to find clouds that are invisible because they look the same as the ice or they're the same temperature as the ocean. There's different channels that serve different purposes. Pretty powerful stuff. So we've gone through this and that. Now, am I running out of time? Did anybody ever want to leave here? Superstorm Sandy. So why polar orbiters should matter to everybody? In some fantasy world, you could be being questioned by Congress, and they say, the American people are sick of you wasting our money. Why do we need a satellite called a polar orbiter? My people live in New Jersey or whatever. Show me why I should care about a polar orbiter. And you'd say, well, Senator, thank you for the question. This is why you should care. Superstorm Sandy affected New Jersey, and because of polar orbiter data, the warning was able to go out sooner than it otherwise would have. We'll prove that right now. Here is a nifty day-night band mosaic of superstorms. There's Sandy over there, and there's Chicago and Minneapolis and such. So this is, you can see, this was people in Wisconsin that did this. But you can see the edge of one pass. They've been stitched together like a quilt there. So the satellite went by, and then it went by again 90 minutes later, and you put them together, and you get this composite of the day-night band. Pretty nice stuff. There's Superstorm Sandy. Okay, everything we've been talking about so far is using satellites to show something a human being can look at, pretty pictures. informative pictures, actionable pictures. Satellites they do that. They also do more than pictures. They also have instruments that sense the atmosphere, the vertical profile, say, of temperature and moisture in the atmosphere through a sounder profile. That's maybe less intuitive to look at when you're a human being, but guess what? Those computer numerical models, as they say, the models love that suite of data from the satellites. So satellites give us pictures for surveillance of weather for humans to look at and understand. It also feeds data that doesn't make pretty pictures, but it feeds meaningful data to these computer models. Because a computer model has the same problem when it answers the phone and someone says, what's the forecast for later? The model, the computer simulation has to know where everything is now at time equals start before you can tell the model to move things around. You have to tell the model where stuff is, and the satellites help feed the model. We're going to look, the pesky Europeans. Europeans have a nice computer model, too nice. The Europeans and the United States, we are frenemies because they have a nice model and we've got a nice model, and their nice model is always like 18 months or 2 years better than ours. I don't work for the Weather Service anymore, so I can say that. But it's frustrating because the Americans, we're getting better with our models, but by the time we catch up to the Europeans' kind of quality, they're getting better too because everybody's always learning. The Europeans, after Superstorm Sandy, it turned out that the European model and the American model had a pretty good forecast on the track of Sandy, even 120 hours, 5 days out. When Sandy was over Cuba, the models were saying, they started to catch on to the idea, hey, Sandy might hit New Jersey, 120 hours out. After the fact, the Europeans, months later, as a study, they said, let's run that model again and keep everything the same, except we'll hide the satellite data from the model. So the model can use the weather balloons, the model can use the radar, can use everything it had before, except we're going to take away the satellite data. This is called a data denial study. And we're about to look at the results of this. This is what you take and say, this is why we care. Here we go. This is the actual forecast. It was made 120 hours in advance of where Sandy's going to go, and it's pretty much on. It actually went a little bit up there, but that's not bad. For 105 days out, 120 hours, the track forecast of hurricanes is gotten so much better just in my lifetime. But here's the same exact model, rerun later. Everything is the same, except they deprived the polar orbiting satellite data from the model's understanding of the first start of the atmosphere. And look, it's totally wrong. This forecast, the storm stays not just out to sea, but way out to sea. Where this bullseye is looking at sea level pressure here, so that's a bullseye, a low pressure. And with satellite data, good forecast. Without satellite data, bad forecast. It's a polar orbiter satellite too, but it matters to the entire United States, matters to the whole world. That's the only way you can get good global quality forecasts is with that polar orbiter data. So I feel like I'm really preaching now, but I'm concerned that people don't really value these satellites for what they do. And this is kind of a hidden background function of satellites, because it wasn't a picture that made this happen, but it was data, and that's still important for the results that we care about. If you're Governor Christie and you want to evacuate New Jersey or not, it's nice to have an accurate forecast as opposed to a bogus forecast. Okay, High Latitude Proving Ground, HLPG, that's another acronym. NOAA, by the way, is National Organization for the Advancement of Acronyms. And I guess every discipline has its jargon and such. Well, what do we do with this High Latitude Proving Ground? Here's the idea. We want to help the Weather Service, Alaska Fire Service, the decision makers, help Alaskans every day in ways that matter to our real lives. Science for the sake of science is fun and powerful and leads to good places in the long run. And also, though, with the satellite proving ground, we're trying to have an immediate benefit as well. What can we do today that helps out? So, a polar orbiter satellite flies over Alaska. There's an antenna farms maybe a bit grand at the university, but we can grab the data from, say, that day-night band satellite, right as it goes overhead. You grab the data from the satellite, you take it downstairs in our building at GINA, and you crunch those data and turn it into a product. And now you've got something a forecaster can look at, and then we hand it to the National Weather Service in Fairbanks, which is right in the next building, and say, here you go, and they look at it, and I showed some of the screen captures of that. You can do this by the time the satellite goes overhead, now the clock starts, in tens of minutes, just 10, 20, 30, even 30 minutes now. I don't think we're that slow, because we're getting faster machines. But you can hand that to the Weather Service, and they've got it in under a half an hour. And then they hand it to Anchorage and Juneau and all over. So you get the data, you make a product, and then you hand it to somebody in Alaska, Weather Service via the websites and their infrastructure. The big idea here is that you want to get this cutting-edge, brand-new stuff into the hands, in front of the eyeballs of someone who can really make the most of it there. And I think for the most part we're succeeding. We still have challenges though. Bandwidth is always an issue in Alaska, but it's always getting better too. And then some of these products, the first time you look at them, we're going to show some really weird stuff. You know that the pink and blue stuff to discern clouds from ice? At first, it takes a little bit of learning to understand, well, which color, what's pink mean again? Some of it's even less intuitive the first time you look at it, so there's a learning curve. But I think despite some of these challenges, it's only getting better here. And ideally, more satellites are going up. There's a new generation of geostationary bird that's going to go up there in another couple of years. They call it GOES-R, they're going through the alphabet. And that satellite, the current imager of GOES that we have, has 5 channels in the imager. The new generation that they're going to launch will have 16 channels. This is good. This is great. This is like, going to cable TV. There you go. Well, here's an example. One of the very first images that we ever made. This was captured and processed at GINA, a successful product, just 2012 April, not even 3 years ago. But this is a fun one. We see Alaska. There's a nice corkscrew down there, some ocean stratus. This is one of those images that is less intuitive. We're zoomed into southwest Alaska. This image is a combination of 4 different channels of infrared. The combination is done in such a way that we're down in, so here's Bristol Bay here, Lake Iliamna. And the idea is we've done the color enhancement such that the really chlorine gas looking ugly green yellow stuff, that should correspond to low ceilings and visibility. This product was generated with aviation in mind. Alaska is big for aviation. And so here it turns out, guess what? We've got 2 miles or 200-foot ceiling and 1/4 mile visibility down here. 5 miles, or 500 feet, sorry, I keep mixing that up, and 10-mile visibility there. We're down to 304 here. So we've got some MVFR and IFR for the aviation enthusiasts down here. So this product is still experimental. In fact, at the end of February, we're finishing a formal evaluation of this new product with the Weather Service here in Alaska. This actually was dreamed up by some folks in NASA in Huntsville, Alabama, and it's their software that we run on machines at the university here, and using our data and their software to create this product for Alaska to ship it to the Weather Service in Alaska. And it's got exciting potential for the future. Of course, nothing is perfect. This product wouldn't look so good if higher clouds were obscuring it. They would get in the way. But what we're seeing here is this is clear ground. You can see Lake Iliamna. And the clouds here are an aviation hazard. So this is a successful image. Well, here's some of these references. And correct me if I'm wrong, this slideshow will be available on the website, I believe, and so you don't have to copy this all down right now, especially these longer ones. But just going from top to bottom, here's some of the GINA things right here at the University of Alaska to get some local data. This stuff's pretty raw on the feeder site, but it's fun to look at and it's current. Here, the Jetstream Weather School is the Weather Service, it's actually in southern region, as they call it, down like Texas and eastward. They've got a nifty website. It's just right for people who aren't meteorologists but want to learn legitimately scientific stuff about the weather. Chapter 13 is not about bankruptcy here. That's their weather satellite channel or remote sensing. So go to that to learn more about satellites. And then this is METED. It's a great website there with different levels of complexity. If you want to see some differential equations, you'll find them. If you don't want that, you'll find that too. So METED it's a great resource. It's free. You do have to register and make an account, but I think that's a great resource. Also, Wisconsin-Madison does some great stuff. Colorado State University, my alma mater, they're doing great stuff. And here's that NASA SPORT is what they call themselves. That stands for Short-Term Prediction and Research Transition, I believe. It's an acronym soup. But they have a good blog, too, showing the latest satellite products there. And no presentation would be complete without this. The moon is our most natural satellite up there. This is the famous Earthrise picture from December of 1968, Apollo 8, when they came around. And the moon is further away, 250,000 miles. It takes that a whole month to go around the planet, obeying the strictures of Mr. Kepler again. And that's, you are here. I'd rather live there than here. So that's beautiful. I made it. We're done. Are there, yeah.